Hello, this is Raymond Seda. I'm going to discuss my machine problem using Bairstow method application. Bairstow method. In numerical analysis, Bairstow method is an efficient algorithm for finding the roots of a real polynomials of arbitrary degree. So this is actually the interface of my program. As we can see here, uh, this this is the area where we have to put the value. I'm gonna be showing. I will show you this one in. We can see it in my program actually. So the initial value of R is also here. Initial value of S is also in this area. The absolute value, we should assign the absolute value and the decimal places. And once we put all the values, we should click the calculate. So the needed inputs, as I mentioned, coefficient indicate the coefficients of polynomial of degree n separated by comma as follows. So an minus 1, an minus 2, and so on and so forth, a1 and a0. So R, this is the initial value of R, and S, this is the initial value of S. So EA is the absolute error. Iteration terminates when the value is reached or less than to this value. So this is very important. Whenever we put here, so once it's reached, the iteration will stop. So the decimal places, which is this one, a decimal digit, round off digit for calculation. So we get also the limitation. This program computes for two roots of the polynomials of degree n per run. If n is greater than 3, you need to rerun the program by indicating yes at the end of each run. So these are the problem that we are going to solve. So x squared minus 4x, x cubed minus 4x squared plus 3x minus 1, which is here. So since this one is x cubed, we have to only put 1 comma minus 4 comma 3 comma minus 1. So once we put all the values, it will automatically, the program will automatically give us the function of x is equal to 1, x, actually this is 1 x cubed because it reads this value, minus 4x squared plus 3x minus 1. It will automatically assign the values here. So since the initial value of r is equal to 0, so we just put here 0. Initial value of s is 0, and the error, the absolute error is 0.0075 with the decimal digit of only 4. So once we click the calculate, it will show us the first iteration, which is having the value of a0 is equal to minus 1, a1 is equal to minus 3, a2 is equal to minus 4, and a3 is equal to to 1, which is all equivalent to b and c. b0 to b3 and b0 to b to c3 are all the same. So as I mentioned, so after counting the first iteration, so we get the linear equation, which is c2 times the value of r plus c3 times the value of s is equal to minus b1. So c1 times the value of r plus c2 times the value of s is equal to minus b0. This is actually c1. So the program only reads the c underscore 2. So in reality, it's actually c2 and c1, c3, c2, b1 and b2 and so on and so forth. So after that, the generated linear equation is equal to minus 4 times the value of r plus 1 times the value of s is equal to minus times 3. So 3 times the value of r plus minus plus times minus 4 times the value of s is equal to minus times negative 1. So therefore, we get a new value of r, of 0.8462 and the value of S, which is equal to 0.3846. So the absolute error value of R is equal to 100, as well as the absolute error value of S is equal to 100. So in the next iteration, we're going to use this new value of R and S. So in the second iteration, we get A0 is equal to -1, A1 is equal to 3, A2 is equal to 4, and A3 is equal to 1. So B0 now becomes -1.6072, and B1 is equal to 0.716, B2 is equal to -3.1538, and B3 is equal to 1, and so on and so forth. Sorry for that. So, therefore, we get a linear equation which is this one, and a generated linear equation of -2.3077 times the value of R, the new value of R, plus 1 times the new value of S is equal to -0.716. So, -0.8521 times the new value of R plus -2.3077 times the new value of S is equal to minus times -1.0, 6072. So therefore we get the new value of R of 0.0073, and the new value of S is equal to -0.6991. So we get the value, the absolute error value of R is equal to 0.8547, and absolute error value of S is equal to 222.2835. So using this new value of R and S, we will going to be using this one for the next iteration. So in the iteration number 3, as we can see here, the value of A0 up to 3 and value of B0 up to B3 and C0 up to C3 are all here. So we get a generated linear equation of -2.2931 times the new value of R plus 1 times the new value of S is equal to minus times 0.0001, and we get -2.2715 times the new value of R plus -2.2931 times the new value of S is equal to 0.0103. So therefore we get a new value of R is equal to -0.0013, and the new value of S is equal to -0.0031. So we get now the new absolute error value of R is equal to 0.1583. The absolute error value of S is equal to 0.9903. So again, we're going to use this value for the next iteration. So in the iteration number 4, we get the value of A0 is equal to -1, and so on and so forth. So we generated a linear equation of -2.2958 times the new value of R plus 1 times the new value of S is equal to -0. So -2.2739 times the new value of R plus -2.2958 multiplied by the new value of S is equal to 0. So therefore we got a new value of R and S which is all equal to 0. So the absolute error value of R is equal now to 0.0002, and the absolute error value of S is equal to 0.0004. So now, as we can see here, the iteration has already been stopped because we already reached the absolute error, which is 0.0075. Now, using the new value of R and S, we're going to compute the root formula using x is equal to R plus and minus square root of Rn squared plus 4s all over 2. So after solving the root formula, we get an imaginary root found. So we get two root, which is 0.8521 plus and minus I mean 0.426 plus and minus 0.3691i. So using the synthetic division to the reduced degree of polynomials, currently it is only reached to 3. So again, using the value of x, which is 0.426 plus 0.3691i, and also minus 0.3691i, we get the new root value of minus 3 point x is equal to x minus 3.148. So now we get all the roots found as I mentioned, 0.426 plus and minus 0.3691i, and x, and the third one is x is equal to 3.148. So all the roots are found, so no need to rerun the Bairstow method. So it means that there's nothing to rerun in the program. You don't need to click the rerun because all the roots are found. Otherwise, if you use the fifth degree of polynomial, you have to click the rerun again. So let's discuss about the source code. We developed this console application in C#.NET using Visual Studio Community 2019. We start the program by calling a method that we created, which is the Bairstow method. For initial run, the program will ask to input the coefficient of the polynomials, the one we want to solve. This must come in a format of an, an minus 1, an minus 2, so on and so forth, and a0 and a1 and a0. And also we split the input and store it in coefficient in the list called a cube. This one here, a coep. So it's all stored here temporarily. If the first coefficient is 0, the program will throw an error. So it means it will not calculate any coefficient which is started to 0 and return to the application. If the number of coefficients is less than 4, we also throw the error. So it means program will also not run. That the error will say that the minimum polynomial is 3. Hence, the number of coefficients we can enter would be at least 4. Initial value of r and s, as the program will also ask the initial value of r and s, as well as the absolute error. So that is very important. And the decimal digits. So we have the base for calculation. Then once all the variables are entered, we can now proceed to the iteration. So we have to click the calculate. So it will go to the iteration, as we can see here. So once after 4 iterations, as I discussed before, so we reach the absolute error value, which is 0.0075, which is here. So the iteration already stopped because absolute error has been reached. So we can also see here the generated linear equation here, which is these are the formula, and the generated the linear equation and also the generated linear equation are also here. Now, after the iteration stop, we now have the final value for R and S. These values are used to compute for the root using the root formula, which is x is equal to r plus and minus the square root of r squared plus 4s all over 2. Now that we have the two roots, and the program temporarily stored these values to a list of all roots. As you can see here, there are root 1 and root 2. Root 1 and root 2, all the values are temporarily stored here. We then proceed in the synthetic division to reduce the degree of the polynomials using the root that we just found. So here, it will calculate the synthetic division using the root that we just found. Once reduced, we check if the new degree is 3 or quadratic, and so we can use quadratic formula to compute for the rest of the remaining roots. Otherwise, we will display the new coefficient of the depleted polynomials. At the end of the programs, it will ask you to reset or quit the application. So, if you need to again calculate, you have to press the reset again to do the first calculation. Otherwise, if you don't want to compute anything, you can quit the application. Other function coded in the program, we have the rerun to rerun the program using the reduced polynomials. Reset will start the program from the very beginning of the execution, almost equal to, due to some machine approximations, we create this method to check if the two numbers are almost equal. This is the end of my presentation using Bairstow method application. Thank you.